Hello, ladies and gentlemen. Today we're going to learn about a special rule called L'Hopital's rule that allows us to evaluate limits in certain conditions. So you can see there's two different spellings. The first one is the one that's kind of more commonly seen and referenced in textbooks. And then the second one here is more a more modern form of his name, believe it or not. So both of these are acceptable and should be recognized as a rule that is going to, like I said, help us to evaluate limits in certain conditions. So let's get right to that. Okay, so this rule says that suppose f and g are differentiable and the limit as x approaches a of f of x over g of x is equal to 0 over 0, or the limit as x approaches a of f of x divided by g of x is equal to infinity over infinity. Okay, so we've seen both of these cases before. We've seen a case where you have a 0 over 0, or call it indeterminate. We've also seen infinity over infinity. And when that happens, we had some different strategies, especially for the 0 over 0. We would try to simplify, factor the numerator and denominator, cancel out that problem factor, and then plug in our a value. We would rationalize if it was a radical, or we would try to combine like terms or do something of that manner. If it was a complex fraction, we would try to simplify that fraction. So the question arises, though, what happens if one of those strategies is we're not able to employ those? Then what do we do? Can we just not figure out the limit? Well, L'Hopital's rule allows us to figure out that limit even if one of our other strategies doesn't work. And this is how. Okay, so this is telling us that the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f prime of x divided by g prime of x. So basically, the rule says that the limit of a quotient of functions is equal to the limit of the quotient of their derivatives, provided that the above conditions are satisfied. So it has to be one of these conditions where you start off with a limit that's going to equal 0 over 0 or infinity over infinity. Those are the two cases that will be tested on your exam. Those are the two cases that you need to be familiar with. And this is the rule that allows us to evaluate those limits. So let's go ahead and get started with some examples. Okay, so we're going to get started with a very simple example to begin with. And this example, actually, we could have solved this using our alternate method. Of course, if I wanted to solve this, I want to first of all make sure that it's a 0 over 0, that I can't just plug in the 2 to begin with. So, of course, 2 squared is 4, plus 2 is 6, minus 6 would be 0, and 2 minus 2 is 0. So this is a 0 over 0 type, which tells us that we're going to go ahead and employ the new rule. Now, like I said, this is one where I could have, and I would have, and you still can, factor the top and factor the bottom, and x minus 2 would cancel out, and then plug the 2 in. But some of you may find that L'Hopital's rule is actually a lot easier. L'Hopital's rule tells us that we can just do limit as x approaches 2 of the derivative of the top function, which would be 2x plus 1, over the derivative of the bottom, which is just 1. Now we go ahead and plug in our 2, and we get 4 plus 1 is 5 over 1. So the limit as x approaches 2 is 5. The second example kind of shows us a little bit more firsthand why we'd even need to know this rule. Because if you look at the second example, again, when I plug the 1 in, I get 1 to the 9th minus 1, which is 0, and I get 1 to the 5th minus 1, which is 0. So it's again a 0 over 0 type. Well, this one, if I had wanted to use my old simplification techniques, I cannot factor x to the 9th minus 1 or x to the 5th minus 1 so that I can cancel out that problem factor. In which case, up to this point, I would just have to say, I'm not sure. I don't know what the limit is. I could look in my calculator, I could do some other things, but I can't do it algebraically. Well, now using this rule, we can. So now we just do limit as x approaches 1 of, take the derivative of the numerator, which would be 9x to the 8th. Derivative of the denominator would be 5x to the 4th. And so when we plug in that 1, we get 9/5 as our answer. Okay, in number 3, we have limit as x approaches pi over 2 coming from the right of cos of x over 1 minus sine x. So L'Hopital's rule does work for all sorts of evaluating limits coming from the left, from the right, positive infinity, negative infinity. So we are able to look at it in all sorts of ways. Here, again, I would plug in the pi over 2. Always have to do this to make sure it is one of these two types. And so cosine of pi over 2, well, if I think about my cosine curve, okay, of course, looks like this. So cosine of pi over 2 is 0. And sine of pi over 2 is 1. Oops. So 1 minus 1 would again be 0. So yes, it is that type. And so we're ready to go ahead and do the limit as x approaches pi over 2 from the right. The derivative of cosine is negative sine x. And the derivative of 1 minus sine x would just be negative cosine x. At this point, if I think through it, if I'm going to plug in that pi over 2, the numerator would now be negative sine of pi over 2, which would be negative 1. But the denominator would still be a 0. And that seems to be a problem. So then I want to think, is there another way I can approach this? And I want to take a look, especially with trig functions, at the function I'm looking at. So I have negative sine x divided by cos x. I should be able to recognize that that's the same thing as saying limit as x is approaching pi over 2 from the right of tangent of x. And now I think about my tangent curve and what it looks like. And hopefully you can visualize it in your mind. And I know that my tan x curve has, in fact, an asymptote at pi over 2. And that my graph looks like this. So it kind of goes up here, down here, and on the other side it would be coming down. So if I'm looking at the limit as x is approaching pi over 2 from the right, that would of course be from this direction, that would be negative infinity. So my answer here is in fact negative infinity. And that, how do I know that, or how do I recognize that? Well, that's one of those things where I would, when I plugged in my pi over 2 here, at this point, I'm still getting a 1 over 0, and that, I don't like that, or a negative 1 over 0. And so then because it is a trig function, I can think, can I write this in another way? And hopefully sine x over cos x you can recognize as tan x. Okay, number 4, limit as t is approaching 0 of e to the t minus 1 over, oops, I just realized I wrote that wrong. It should be over 3t. All right, so let's go ahead and approach this. So again, if I plugged in my 0, I get e to the 0, which is 1 minus 1 is 0 over 3 times 0 is 0. All right, so I apply my rule that limit as t is approaches 0 of the derivative of the top. Well, the derivative of e to the t is just e to the t, and then the minus 1 would go away, over the derivative of 3t is simply 3. So now when I plug in my 0, e to the 0 is 1 over 3. And so my my limit is 1/3. All right, let's take a look at the next one. So I have limit as theta is approaching pi over 2 of 1 minus sine of theta over cosecant of theta. All right, so we just talked about 1 minus sine of pi over 2 would be 1 minus 1, which is 0. On the bottom, cosecant of theta. Okay, now we know cosecant is the reciprocal of sine. So if sine of pi over 2 was 1, the reciprocal of that would still be 1. So in fact, this one does not need to use L'Hopital's rule at all. And I'm doing this on purpose because I don't want you to just jump in ever. You always have to mentally make sure you get the 0 over 0 type or the infinity over infinity type, which is not quite as frequently used. But if in this case, the limit would simply just be 0 and you'd be done. So you want to be careful to not just jump in, but always to make sure that you're checking to make sure that you have just cause to use that rule. Okay, the next two, we're looking at our limit as x is approaching infinity and seeing how that affects the problem. So with limit as x is approaching infinity, generally you're going to end up with an infinity over infinity. So obviously infinity plus infinity is infinity, and then 1 minus 2 times infinity would be negative infinity, but we're not going to, you don't need to worry about if it's positive or negative. You just need to worry about if you will get an infinity over an infinity case. And so in this case, now we already know the rules as the limit as x is approaching infinity, and honestly I think that it's probably just as easy to use the power fight rule, but the reason I'm showing you this is because I could totally see them asking a question on the short response, asking you to justify that the limit is equal to, in this case we would know that the power fight here is x squared and x squared is winning on the top and bottom. So your limit as x approaches infinity is simply the ratio of the coefficients. So we know it's going to be 1 over negative 2 or negative 1/2. But if they asked you on a free response question to justify using L'Hopital's or justify and state the rule that allows it, then you're going to have to know how to use L'Hopital's rule in this case. So let's go ahead and take a look at see what happens. All right, so following the rule, it would be limit as x is approaching infinity. Derivative of the top would be 1 plus 2x. Oops, and derivative of the bottom would just be negative 4x. Okay, now at this point, if you plug in your infinity, you still are at infinity over infinity. So that has not helped. So guess what? We can go again. If when you apply L'Hopital's rule a first time, you still end up with that indeterminate case of 0 over 0 or infinity over infinity, you can go again. And so now we apply the same rule again. Limit as x approaches infinity of the derivative of the top is now 2 over the derivative of the bottom is now negative 4. And now I can see that obviously it's negative 1/2. So like I said, this to me is definitely a longer way to do it, and I would definitely use the power fight whenever I'm looking at limits at infinity. But if they ever asked you to justify or to show by using L'Hopital's, now we've hit on an example that you have to fall back on. All right, number 7, limit as x is approaching infinity of natural log of x squared over x. And so here, again, if I put an infinity, I would definitely have infinity on the top and infinity on the bottom. All right, so limit as x is approaching infinity of. All right, this is the chain rule here. If I take the derivative of natural log of x squared, it would be 2 natural log of x to the first times the derivative of the inside would be 1 over x. Over, derivative of x is just 1. Okay, now if I take a look at this, I end up with a fraction in my numerator, which if I were to rewrite, it would be the limit as x is approaching infinity of 2 natural log of x over x, right? That 1 over x can be, that x can be pushed down, or think about it multiplying the numerator and denominator by x. Well then now, if I put infinity in, again I'm going to get infinity over infinity. 2 natural log infinity is infinity over infinity. So apply L'Hopital's rule one more time. Limit as x is approaching infinity of 2, the derivative of 2 natural log x would be 2 over x, or 2 times 1 over x, over 1. Okay, now I'm ready to plug in the infinity. So we have to understand the concept that when you plug in infinity in the numerator here, you're plugging it in as 2 over infinity. Well, 2 over an infinitely large number is going to be exceptionally close to 0. And so when you have any constant number divided by infinity, we can go ahead and say that that is going to be 0 on the top, and then obviously over 1. So your final answer here is equal to just 0. Okay, number 8. I actually would like you to go ahead and pause the video and try number 8 on your own and come back and you can compare your answer with mine. Okay, so if we take a look at this one was definitely an involved one. So stick with me here as I go through it. Okay, so first of all, I went ahead and plugged in my 1. 1 minus 1 is obviously 0, plus natural log of 1 is another 0, so 0. Over 1 plus cosine of pi times 1 would be cosine of pi. Cosine of pi is negative 1. 1 plus negative 1 is 0. Okay, so I started off with the 0 over 0 case. So I used my L'Hopital's rule and I took the derivative of the numerator. The derivative of negative x is negative 1. The derivative of natural log of x is 1 over x. Over, the 1 goes away. Derivative of cos pi x would be negative sine pi x times pi. Okay, I just kind of cleaned that up for a second and rewrote it. So I wrote it as negative 1 plus x to the negative 1 over negative pi sine pi x. Now, I'm ready to plug in the 1 and see what happens. When I plug in my 1 on the top, I get negative 1 plus, well, 1 to the negative 1 is just 1. So negative 1 plus 1 is 0. And when I plug in 1 in the bottom, I notice right here, sine of pi is going to be 0. And so 0 times negative pi is 0. So again, I get that 0 over 0. And so like we've seen in the past, if using L'Hopital once doesn't work, go again. And so took the derivative of the top. So limit as x approaches 1 is now negative 1, x to the negative 2 is the derivative of this, okay, because again, this one would just go away, and x to the negative 1, its derivative is negative 1, x to the negative 2. The derivative of the denominator, negative pi stays, derivative of sine is cos, keep the inside, times the derivative of pi x is pi. So now I go ahead and plug in my 1 on the top. I just get negative 1, right? Negative 1 times 1 to the negative 2 would just be a 1, so negative 1 on the top. On the bottom, okay, I have this negative pi and this pi, which makes negative pi squared. And then cosine of pi, because pi times 1 is pi, cosine of pi is negative 1. So I have negative pi squared times negative 1, which is positive pi squared, and negative 1 on the top. So my final answer is negative 1 over pi squared. That one was definitely involved. Okay, so if you got that right, that is fantastic. If not, it's understandable, and we're going to keep working on ones like that so that we can get them next time. All right, let's take a look at one last question. Okay, the last one we have here for you, the limit as x approaches 0 of x over the inverse tan of 4x. All right, so let's take a look at this. Obviously, we get 0 on the top. Okay, inverse tan of 0. Well, inverse tan of 0 is saying at what angle measurement is it going to give me back a ratio of 0. And if we go back to that tangent curve we drew quickly a few questions ago, I know that tangent of 0 is equal to 0. And so therefore I can see here that this is going to be a 0. All right, so that means that I'm going to have to use L'Hopital rule, and its limit as x is approaching 0. Derivative of x is 1. Okay, derivative of the inverse tan of 4x. So from last video, we know that derivative of inverse tan is du over 1 plus u squared. So du here would be, if this is my u, okay, du would be 4 over 1 plus 4x squared. All right, so now I'm ready to go ahead and plug in my 0 and see if that worked. So I still have a 1 on the top, and on the bottom I would have 4 over 1 plus 0 squared. So that would just end up being 1 plus 0, which is 1. 4 divided by 1 is 4. So we end up with an answer of 1/4. So that one ended up being a lot easier than it looked like, as long as you remember the inverse tan derivative formula. All right, thanks so much, guys. We will definitely practice these more in class next time. But make sure that you can come in knowing what L'Hopital rule is, when are the conditions when you would use it, and always, always, always remember to check to make sure you get one of those two conditions before you just jump right into the problem. Okay, thanks a lot. See you next time.